Okay, we are allowing 1 more minute or 2 minutes for more people to join. We're also still waiting for Randy. Hopefully he found the link. Okay, more people are joining.
Yes. Yeah, that's right.
Did Dr. Salem already, did he join already or not yet? Because he's the first speaker in the session. Yeah, so until he, yes, yeah, okay. It's nice. So we are still missing Greg and Randy. Yeah. Hi, Dr. Salem. Yes, and we have Anna. So yeah, we almost, yeah, close to complete our speaker list. Hi, Anna. Okay, just we are missing Randy, and I'm just emailing the link to him. Okay, so we can start now, and while we are starting, I can indeed ping them again. Okay, I'm just sharing my screen. Okay, so welcome everyone to the Quantum AI #7 monthly series. Today we are going to have very exciting talks together. Mr. Yusuf Dakar and I, we are going to present to you well-respected and very nice speakers from all over the world, bringing to you the quantum excitement and the new quantum achievements and also innovation, and also the excitement of discussion indeed. And today we have speakers. We are going to start by Dr. Salem, and then we are going to end up with Mr. Jan Plumart. This week, we had a quantum summer school to prepare for the hackathon. So we have a hackathon in the upcoming week. We have planned that hackathon in Bibliotheca Alexandrina since last December. It was very promising plan. And now we are about to have the hackathon at the end of this phase. That's going to start next week. This week, we have the Quantum Summer School to prepare everyone for the hackathon, but also for other applications in quantum computing as well. And there is variety of excited topics and very interesting topics like the quantum mechanics, hands-on and machine learning, quantum machine learning, quantum annealing and optimization, quantum chemistry, and also how to use and the qubit environment for running quantum programs. So today we have a very nice schedule. We are going to start by Dr. Salim Higazi, who's going to talk about quantum processing in photonic degrees of freedom. Then it will followed by a talk by Dr. Randy Kyong about the quantum permutation pad with random number generator, which is a true random number generator based on quantum principles. Followed by a talk by Mr. Alain Chancey, which is rated as a quantum permutation pad, and he's gonna present a very nice demo from noiseless simulation to running on a real quantum processing unit. And then I'm gonna present a short talk on the quantum computing for chemistry and chemistry simulations and quantum molecular dynamics and the relation between quantum molecular dynamics and quantum computing. This will be followed by a talk by Mr. Greg Pitts, who's going to talk about a very exciting, nice topic, which is prominent and well propagated in the industry, the quantum computing and the future of cybersecurity, the fear of the Q day, or the disaster day for cybersecurity. Then after that, we are going to have the question and answer. In the question and answer, we will be having Mr. Jan Blomert, and he's going to also help in answering questions related to the quantum technologies and the quantum industries. Now we have the hackathon next week. Allow for me to introduce my colleague here, Engineer Yusuf Al-Dakar. Engineer Yusuf Al-Dakar is the head of the International School of Information Sciences at Bibliotheca Alexandrina. He has a current role, works to provide support to research through the technologies of parallel computing, big data, natural language processing, and visualization. He also worked in the high-performance computing and is still working till now. He was assigned in 2013 to lead the Bibliotheca Alexandrina HPC service, providing a platform for high-performance computing to researchers in Egypt at times regionally through European collaboration. He also led several nice projects like the web archiving, worked with Brewster Kahili in 2002 to deploy the first Bibliotheca Alexandrina web archiving cluster, continuing to lead the Bibliotheca Alexandrina's work in web archiving. Also, he represented Bibliotheca Alexandrina, the International Internet Preservation Consortium, since 2011, and he's a member of the steering committee since 2018, lead of the tools development portfolio since 2021, served as consortium chair in 2023. He also led the project book digitization, contributed to book digitization during the initial phase of the efforts at Bibliotheca Alexandrina, and then started projects like LinkGate for larger scale temporal graph visualization, started project NoAdmin for HPC account automation, also led several Bibliotheca Alexandrina internships and internship programs for students of computing, and he was profiled in Marcus Who is Who in Science and Engineering. So welcome, Engineer Yusuf, and the floor is yours to give nice words about. Yeah, if you like.
Thank you very much, dear Dr. Taha. And I think that the key thing to highlight this time is a note of thanks to the community and everyone in the community who has taken on the mission to take this through all the way till now, and we're just a few days away from the hackathon. We like to think of this hackathon as a booster, a milestone along the way, and we look forward to continuing the journey after that with this wonderful community to build capacity in this domain of quantum computing and AI, and put this technology to use to solve problems and make good things for society. So it's really another thanks to everyone, and of course, special thanks to my dear friend Dr. Taha, who has put a lot of effort and very nice preparation and organization of everything. So we look forward to next week. Those of you who will be coming to Alexandria and the library, we look forward to welcoming you there. We're very happy that we had several virtual events preceding this hackathon, including the dry run, which was about a month ago, and just this week, concluding the summer. Strong willingness to teach and to learn and to develop. It's really something to continue to look forward to. So thanks again, and I'll leave the floor to our wonderful speakers to start this 7th edition of the multi-series. Thank you.
Yeah, thanks very much, Engineer Yusuf, for the nice introduction and highlighting the work in the hackathon. And I would like to take this opportunity to thank our also excellent team who's did very and also still doing great work and the progress. You are gonna see all of them in the hackathon, including also Bibliotheca Alexandrina's team, who's also doing an excellent work in executing the hackathon.
Thank you very much. Thank you.
So now we are moving to the our first speaker. So, and our first speaker is Dr. Salim Higazi, and he's going to talk about the quantum processing in photonic degrees of freedom. So welcome, Dr. Salim. Dr. Salim Higazi received his bachelor degree. It is an honor degree, and a diploma and a master degree from in electronics and communications engineering from Cairo University in 2002. And he received also the diploma in 2006 and the master's in 2011, respectively. And he did his PhD degree in quantum optics and the quantum information in 2017 under a joint supervision scheme between NILS and the National Institute of Laser Enhanced Sciences at Cairo University and CREOL, the College of Optics and Photonics at the University of Central Florida. He served as the head of the Laser Engineering Department at the National Institute of Laser Enhanced Sciences at Cairo University from 2022 to 2025. And he was also a research associate and the founding director of the Quantum Communications and the Cryptography Lab at the Wales City of Science and Technology. Since 2025, he has been an associate professor with the Information Technology and the Computer Science School at Nile University. His research spans optical processing of quantum information, photonic quantum computing, practical security of quantum cryptography, quantum random number generation, quantum photonic simulator, and photonic entanglement, optical communications, optical chaos-based systems, and optical image encryption. He was the recipient of the State Encouragement Award in Engineering Sciences in 2019 and the State Award for Organizations and Individuals in Scientific and Technological Innovation in 2021, among others. So welcome, Dr. Higazi, and the floor is yours. I'm just going to stop sharing my screen.
Thank you so much, Dr. Taha. Thanks for inviting me to Quantum AI session. It's my first time to be here, and I see there is something like 40 people listening to us, so it's very successful and impactful. Thanks very much for your efforts in energizing quantum computing and quantum information science among the students and among researchers. It's a very good opportunity actually for me to be here. So I'll share my screen now.
Yeah, sure.
So I shared that. You see my screen?
Yes.
Okay. Today, my talk will be about quantum processing and photonic degrees of freedom. Why photons are different? They are chargeless, don't interact or weakly interacting with each other, guided along long distance with low loss through different channels, optical fibers, atmosphere, and free space. They can be easily manipulated and delayed at room temperature without any cryogenic difficulties like quantum, like superconducting quantum computing, for example. Using traditional optics, maybe in any traditional lab optics lab in Egypt, something like phase shifters, phase retarders, and mirrors, beam splitters, all of these elements can be used to manipulate the photon state. So quantum photonic systems actually is readily are readily implementable in Egypt without any need for any special experimental facilities. This is important. They are weakly interacting with each other. So we see that we use photons in all or most of our communications now. When you are using your mobile, when you are using Wi-Fi, even if you are using internet now through DSL, all of these are based, are communications based fundamentally on sending photons. Being non-interacting with each other or non-interacting with the environment make photons perfect quantum system for communication and for interaction between distant systems. So typical quantum computing task can be represented like as we see now. We have an initialization stage here, including the generation of quantum system, in our case, generation of single photons and some preparation stage. And then we will have something like a processing stage. This processing stage includes number of quantum gates. Many of them are single qubit gates, like Hadamard here, for example, and other gates are controlled 2 qubit gates, maybe 3 qubit gates. It's not here, but there is 3 qubit gates, 4 qubit gates, and something like that. After unitary evolution of the initial quantum state through the system, till we have at the output here, we have the photons we measure. So measuring these photons, we need to detect the photons. So we need initially to generate photons, manipulate them using optics. Then finally, we need to detect them. So by these stages, we can perform quantum algorithms, quantum protocols. All of these quantum operations can be described by a circuit, a quantum circuit like this one. So let's start by the first step, initializing a quantum state and generation of single photons. How can we generate single photons? This is not a naive question, because natural light sources we have emit thermal light, like sun and fire. This thermal light, bunch of photons, without a mixture, without even coherent superposition between them, slight mixtures, just a mixture of number of photons of different states in different degrees of freedom of the photon. So if we like to talk about something like lasers, the best light source that human has created, have created it. Laser is very pure source, but still laser does not create single photons. If we have pulsed lasers like that, a pulsed laser emits pulses distinct in time. Every pulse of these pulses has some energy. Okay, so if I asked any one of the students to what is the number of photons per pulse, well, he would say, okay, let me know about the energy of every pulse and know about the wavelength or the frequency of this laser. So it will divide the energy of every pulse by h Planck constant multiplied by nu, the frequency. So h nu is the energy of the photon, of a single photon, and we divide the total energy of all photons by the energy of a single photon. In this case, anyone will think he knows deterministically the number of photons within this pulse, within this pulse of laser. This is not accurate. Why? Actually, because this is a coherent state. Lasers emit coherent state. In coherent state, we have no knowledge about the deterministic number of photons by each pulse. We just know about the mean number of photons. The mean, what you have just calculated is the mean number of photons, the average number of photons, not the true number of photons in the pulse lasers. And every one of you may ask, then how can we describe the number of photons in this case? It can be described by something like that, a coherent superposition in focus space. Focus space has bases. It's named after Fock in 1930s. He addressed a space with bases number of photons. So we have n equals 0, positive, non-negative numbers, maybe 0, 1, 2, 3, in principle to infinity. So every number of photons have something like a probability amplitude, and we have a coherent superposition. This is a coherent state. In the amplitude here, we have a summation for all non-negative values of integer number from 0 to infinity. Lambda is the mean number of photons, mean number which you just calculated now. So we have lambda as a mean number, okay, and n is the number of photons in the superposition, and this is the n factorial under square root. We have something like statistics, okay, for the number of photons. Okay, in every quantum algorithm, quantum protocol, we need to have single photon source. How can we generate something like, not truly single photon source, there is not truly single photon source, but we need to generate something like an approximation for ideal cell. This is good approximation if we have an attenuator. Attenuator is just an opaque glass. This attenuator attenuates the pulse, decrease the mean number of photons per pulse, the lambda, to very small values. In this case, we have, as I said here, this is probability amplitude for every number of photons in the superposition of the coherent state, e power minus lambda, lambda by lambda power n over n factorial, and the lambda is the mean number of photons you have just calculated. And now we have probability for each to have each of these numbers. We may have an empty pulse of this pulse may be empty, maybe two single photon or two photon or something like that. Let's see here the figure. If we have, for example, lambda equal 4. Lambda equal 4, you have attenuated this pulse to 4 photons per pulse. So we have a probability that there is no photon at each pulse. You have probability that there is 1 photon only, 2 photons, 3 photons, 4 photons, something like that to infinity. If we have lambda equal 1, for example, we have something like 37% probability of photons, 37% that there is no photon in this pulse, 37% that there is 1 photon, 2 photons, and something like that. Typical example, quantum cryptography. And I mentioned about quantum cryptography because there is a problem here if we have more than 1 photon in quantum cryptography. Because the attacker can split these photons and have one of the two photons or one of these photons to himself to or herself to measure it. We in quantum cryptography typically we reduce lambda by the attenuator to something like 0.1. So there is 90% probability that there is no photons at all. 90% of the pulses have no photons, and 9% only have one photon. And for more than one photon, which may be a problem, we have only 1% of very, very small. Later stages of quantum cryptography, like privacy amplification, try to decrease even more this 1% to very small, negligible value. Pent pulses, as you see, pent laser pulses are not ideal single photon band. It's a basket with only single photon. We have here an example for lambda equal 0.1, and alpha is as a superposition like. So we now know about how to generate single photons, not deterministically, but probabilistic. The main problem here is that if we have two sources of this system, we cannot synchronize it. It's a problem, and it can be overcome by using other types of single photon source, like heralded single photon source using entanglement. Here, we have experimental systems in our quantum communications and the cryptography lab uses CL. We have a laser driven by driver. Okay, this laser emits photons here. Okay, it's not single photon, but very weak signal, very weak pulses. Okay, and emitted here from the fiber these pulses, because we have here an FPGA, as you see, controlling the laser. Okay, running through this SMA cable. So here we have very weak pulses. Every one of them, something like, every pulse is something like 7 nanosecond width. Okay, we have an attenuator here. And after that, a mirror, another mirror, and another attenuator. And then an interference filter that filters out the environmental photons, the background photons, and only single photons emitted from this laser will be detected here by the detector. What you see here is the single photon detector, and then we have a BNC cable connecting this detector by oscilloscope display. Okay. Now you may have good knowledge about how to generate single photons and initialize the states here. Let's move forward, not to the second step, but let me jump this and skip this and go to the other stage, and we will return back to the second stage later. How to measure quantum states. In case of single photon, the basic element is single photon detector. You may say, okay, we have already optical detectors. My mobile detects the environmental background light and turns the brightness display of my mobile, so we have an optical detector on my mobile. Okay, this is the only intensity detector. But single photon detectors are different. Single photon detectors are designed to detect only single photon. Upon receiving a single photon, the single photon detector should generate a pulse for every detected photon. Okay. Here I'll address one of the most common single photon detectors, avalanche photon detector. Here we have avalanche diode, something like p-n junction. Okay, p-n junction, and heavily biased. This is high voltage and large resistance, and another resistance here. All of them are in series. As you see, the avalanche photodiode are reversely biased, okay, and heavily reversely biased using this high voltage. So no current here are passing. Okay, no current here pass through this circuit. But if we have a single photon go to the depletion region of the p-n junction, it will emit, it will generate an electron hole pair. Under the high voltage here, the electron and the hole the electron will go to the positive terminal and the hole will be accelerated to the ground terminal. And because there is high voltage, we will have the electron accelerating and have more energy and colliding with other atoms and other electrons in the valence band and free them to the conduction band. So there will be more and more number of photons going through the p-n junction to the positive voltage terminal. Okay, and passing this current, because this is a series connection, this current will be passing also within the R bias and within the R node. Okay, so initially we have a voltage which is VHV more greater than the breakdown voltage of the diode, and here in the x-axis. Okay, we are here because initially there is no current passing through the avalanche photodiode. But when we detect a single photon, the detector, the p-n junction, the avalanche photodiode will create accelerating electron and dramatically increasing the number of electrons. So we'll have current here. This current will move our point from here to here. Okay, and after that, as you see, this current will pass the heavy resistance, the large resistance R bias. Passing through R bias in a series connection, we will have a voltage potential across R bias, I, the current, multiplied by R bias. Okay, this large resistance, this voltage will take the high voltage from biasing from the voltage across the p-n junction. So we will go from this point to a point in voltage less than the breakdown voltage across the avalanche photodiode. In this case, this will quench the avalanche, and there is no more electrons, and we'll go to zero current, and then we'll go back again to the same point, preparing to detecting another single photon. So every single photon pulse going to the detector will be translated into an electronic pulse of something like 5 voltage height, okay, and something like 20 nanosecond width with some efficiency. So maybe single photon killed here in this process, but no electronic pulse out, something like quantum efficiency, something like maybe 70%, 65% as the central wavelengths of the operation of this avalanche photodiode. So now we know about the generation of single photon and the detection of single photon. I like so much to begin with these two stages to answer many questions in your mind about how to generate single photon, how to detect single photon. Now let's move to the processing part. Hey, we have gates. All of them are unitary gates in Hilbert space of dimension 2, like Hadamard, of dimension 4, like controlled node, for example, and this controlled rotational operation. Photons carry energy, momentum, have spin angular momentum. It's called SAM, abbreviated as SAM, and the photon has polarization and carry as well orbital angular momentum, 1. Okay, the photonic degrees of freedom are space momentum, space, because the photon wave function has some special distribution, and this special distribution is in direct mapping into the momentum degree of freedom, because there is something like a Fourier transform relation between the two spaces, the space and the momentum. Another degree of freedom is the frequency of the photon, the nu. In the visible range, we have nu in something like 1.5 or 1.1 multiplied by 10 power 50 hertz. Frequency represents the energy of the photon when multiplied by the Planck constant. And if we have a spectral wave function for the photon in frequency domain, we can directly map this wave function into temporal domain into time by Fourier transform relation. So the frequency and time actually is the same degree of freedom, like space and momentum. Another distinct degree of freedom is the polarization, spin angular momentum. So photons have 3 degrees of freedom: space momentum, frequency time, and polarization. Any photonic wave function can be described as a superposition of different modes in every degree of freedom. In polarization is a vector, unit vector. So we have a summation of different polarization. We have summation of different frequencies and summation of different spatial wave functions. Okay, with different complex amplitudes. This will describe any wave function we know about. We'd like to describe about photon. So in this shape, we have 3 modes: mode 1, mode 2, mode 3. Every mode of them, every optical mode has a non-negative number, an integer number of photons, 0, 1, 2, to infinity. And between every step and the other of the energy, we will see something like h nu, the energy of photon. Okay, you have 3 photons here, 2 photons in this mode, and something like that. So now, maybe late, but I think this is a proper position to add this slide. What is different between bits and qubits? This may be a very simple question for all of you. By activities like the activity organized by Dr. Taha here, all of you, I know most very well about what is the difference between bits and qubits. Bits described by just 2 points in space, 0 or 1. So it can be described by 2 levels of something very distinguishable. Different phases, for example, minus sine omega t and sine omega t biplation. Bits. Polarization, I can describe 0 as vertical polarization and 1 as horizontal polarization. Okay, it's good. But all of us know that photons support, and the quantum systems, and all quantum systems support the coherence proposition between different modes. So we don't only have H or V. When we move to the quantum domain, we have the superposition between horizontal and vertical phases. We have superposition between H and V, alpha H plus beta V, with square root of 2, square root of alpha modulus power 2 plus beta modulus power 2 equal to 1 for normalization. And this is the unit vector describing the polarization state. The polarization, polarization is 2-dimensional by nature, and the qubit is 2-dimensional. So polarization can directly describe photonic qubits. Let's see here. Let's watch this video about polarization. To know more about this coherence superposition, here we have horizontal and vertical. The blue is the horizontal, and the vertical The breadth is the vertical component. And actually, what is the laser? What is the state of the photon? In this case, the state of the photon is linearly polarized along the diagonal directions, diagonal polarization, D. Okay, we have two polarization with no relative phase. H and V has no relative phase. Alpha and beta are real numbers in this case. Now, adding the phase, relative phase, to the vertical component. Okay. Now, we will see that the resultant of this photon will be, of this photon's polarization state, will be something like circularly polarized, circular polarization state. Photon polarization, naturally described by coherent superposition like that between horizontal and vertical, with alpha and beta being two complex numbers supporting the normalization relation. Okay. So we described the diagonal and the circular polarization. And here we have some famous examples of polarization states. This is the diagonal state we have just seen. 1 over square root of 2 H plus V without any relative phase. The anti-diagonal in the diagonal in 45 degree. Okay, in the 45 degree, and the anti-diagonal in 135. And the right circular polarization with a relative phase minus pi over 2, and the left circular polarized with a relative phase pi over 2. All of us know about logosphere. 1-bit gates can be, I am still in the comparison between bits and qubits. The 1-bit gate can be either buffer or inverter. But 1 qubit gate, infinite number of 1 qubit gate can exist. Why? Because we have infinite number of points all over the surface of this block sphere. And the gate definition is some operation that take the initial state from some point to another state. So, infinite number of quantum gates, but the famous gates you know about, them very, very good. Any gate of any unitary operations, any gate of this can be described by a unitary rotation. So we need only something like an axis of rotation and an angle of rotation to describe the operation of any of them. So, for example, Z gate applied on the plus state will have the axis is the positive Z axis, and the angle 180 arc here, and we will have this result. Okay. It's abstract linear algebra, but how to describe these in optics in the polarization domain we have just described? This optical element is half-wave plane. It rotates the polarization, as you see. The polarization is the plane of the disturbance of the electric field. Now it's vertical in the input, and here it's horizontal in the output. When the half-wave plate is X is rotated by something like a 45 degree, we see it on this graded in this graded scale. Okay. So these half-wave plates as a transfer matrix for polarization state, for polarization qubit, is acting with this transfer matrix. It's a unitary matrix describing the operation of the half-wave plate. How can we use this in quantum computation? If you have this half-wave plate in your lab and you have a laser emitting vertical polarization, okay, just rotate this half-wave plate by some angle theta, any angle theta, and you will have some quantum operation, some quantum gate. For example, if theta equal 45 degree, you will have just substitute with 45 in the transfer matrix. We have just seen in the previous slide, you will have here cosine 90, which is 0, 0, and 1, 1. This is a NOT gate. So just rotating the half of plate by 45 degrees, you have, surprise, surprise, you have a 45, as you have a NOT gate, okay? And if you have theta equal 0, it's only a Z gate, Pauli Z gate. If you have theta equal 22.5, it's Hadamard gate. It's very good because this half of plate, when you see in the lab, it's something like just a glass. But by just rotating it, you will have different quantum gates applied on the polarization, here. Quarter wave plate, if you have a half wave plate and split it into two identical parts, every part of them will be a quarter wave plate. It moves between the horizontal, between linear polarization and circular polarization with some sphere matrix. Okay, Doctor?
Yeah, so Dr. Salim, we just about the time. We are now
It's
beyond the time. Yes.
oh, okay.
Yeah, no worries. Yeah.
So okay, all of these gates can be represented and manipulated using half plate and quarter plate. In time band domain, we can use this heavily unbalanced Mach-Zehnder interferometer to create time band qubits like this one. We have time mode T0 and T1 and T0 and T1, and we have coupling ratios here, alpha modulus, beta modulus. We can create these qubits in time. In another space, in spatial degree of freedom, we can also have this representation, this spatial representation for the qubit. So in path domain, we can build any of the unitary operations we need. So we using just beam splitter with this matrix and phase shifter acting on one of the dual rail on one of the two paths by a phase shift 5. So you may ask, okay, all of these are single qubit gates. What about 2 qubit gates like controlled knots, for example? Polarizing beam splitter, transmitting the horizontal polarization and reflecting the vertical polarization. So if you have photon with horizontal polarization, it will pass through. If it's vertical polarization, it will reflect off. So this represents actually a C0 if we take the polarization as a control qubit and the path as the target qubit, because 0 turns to 1 in case of B and 0 remains 0 in case of B. So all of these degrees of freedom can be used. In case of 2 qubits, it's not direct like the single qubit, generation of single qubit. If we need to create something like entangled state, we can use nonlinear optics, nonlinear crystal, to emit 2 photons from an original energetic bump photon. Conservation of energy and conservation of momentum applied in this case, and we can have, as we will see, frequency entangled photons, frequency entangled that you have, don't know about omega 1, omega 2, but you know about omega bond. So uncertainty about the frequency and the false certainty about the summation creates what's called frequency entangled photons. Momentum entangled photons, you have more conservation of momentum. You don't know about K1 or K2, but you know about the summation of them. So you can create by nonlinear optics, momentum entangled photons. In case of polarization entangled photons, using one crystal pumped by vertical polarized photon, it will generate 2 horizontal photons. So we have this point in the polarization space. It's the polarization of the first photon, second photon. We have HH. If we just rotate this crystal and bump it by horizontal photon, will emit 2 vertical photons. So we'll have these points. So we have 2 points by these 2 crystals, as we see here. If we want to generate polarization entangled photon, we just make both of them apart to each other, adjacent to each other, to create using diagonal polarized photon, generate HH plus BB over square root 2 is the polarization entangled geometry. Okay, I'll skip this. We have here this source creates polarization entanglement and momentum and frequency entanglement. This setup we have in our lab at Cairo University. It generates entanglement in every degree of freedom and violate Bell inequality. Bell parameter is 2.6, for example, plus or minus 0.06. Here we have the laser source and the crystal preparation stage and mirrors and fibers. Till fibers carry the photons to the single photon detectors. Same but older setup here. Skip this. So if for newer versions of entangled photon source, we can use something like this source, 2 crystals, but shuffle and interleave with each other to create a highly pure entangled state. In temporal entanglement, we can find that if photon 1 and photon 2 are entangled in time, we come and going through the beam splitter at the same time. In this case, we'll find that the transmit, and the reflect possibilities will be cancelled out, and we will see that the 2 photons will be collected at one of the 2 boards, which is called Hongo-Mandel interferometer, and it's called the Hongo-Mandel depth, a hallmark for the entanglement in time. Thank you so much. I have finished my presentation. Thank you. If any questions?
Yeah, thanks very much, Dr. Salim. It was a very nice, informative talk. Yeah, thanks a lot for all of the clarification. So, does anyone have any question? Okay, so if not, we thank Dr. Salim again. Thanks very much, Dr. Salim, for the nice talk. And thanks. And we'll be also glad to host you next week in the hackathon in Alexandria. Thanks again. And we move now to our next speaker, Dr. Randy Kyong. And then we have this is a software part, and then we will have the use cases. Yes. Yeah, but then I will just introduce you, Dr. Randy, I'm sharing my screen quickly.
Okay.
Okay, so we have now Dr. Randy Kyong, who will talk about quantum permutation pad with a random number generator. So Dr. Randy Kyong is a visionary quantum physicist, inventor, and entrepreneur who has dedicated his career to bridging quantum mechanics, cryptography, and artificial intelligence. With a PhD in physics, his pioneering work has earned global recognition, including a NASA honor for his early research on electron capture cross-sections. As a co-founder and the chief scientist of Quantropy, Inc., Dr. Kyong drives the development of the next generation quantum secure technologies. He holds over 40 US patents across telecommunications, cybersecurity, and authentication. His most notable inventions include the first 2-level authentication patent, which helped lay the foundation for the FIDO security standard. Dr. Kyong is also the creator of several breakthroughs in innovation, like the quantum permutation pad, QPP, homomorphic polynomial public key HPP K cryptography, quantum permutation pad with random number generator, a true random number generator based on quantum principles, quantum encryption in phase space QEPS for coherent optical security. Crowning these contributions is his quantum cryptographic dynamics QCD framework, a unifying model that supports a complete post-quantum cryptographic ecosystem. Through this work, Dr. Kyung has proposed a quantum secure eco-crypto system architecture, paving the way for resilient cryptography in the era of quantum AI. So, Dr. Randy, the floor is yours.
Okay, thanks very much. So, I can share my screen. Windows. Okay, can you see my screen? Hello?
Yes. Yes.
Okay, so everybody can hear me, right?
Yes.
Yes.
Okay, first, thanks, Taha, that gave me this opportunity to this initial talk. So my talk is virtual quantum reality, a new paradigm for true uniform random number generation. So I'm Dr. Randy Kwong, co-founder and chief scientist of Quantopy. So what is VQR? Basically, VQR is just a conceptual topic. It can be extended for cryptography and security, quantum-inspired computation, quantum simulation and modeling, and also quantum AI, machine learning integration. Or you can, expand to this just a few list. So. For the VQR, we want to get a true uniform random list. So the question is, can random lists produced in software be truly unpredictable? That is a big challenge. We knew this, for example, here at least 3 randomness source, coin flip, this physical randomness. In the past half century, or more than half century, we knew the possibility is 50 to 50 head and tail. But recent, experiments show this 50.8 to 49.2 possibility. So they're not even, it is unpredictable, but they are not uniform distributed. Of course, we knew this pseudo random generator. We have a bunch of these PRNGs. It is a deterministic algorithm, and based on a seed. So all this randomness is reproducible. So once you know the seeds, you know everything. Of course, today we have a many QRNG, quantum random number generator, based on quantum uncertainty. Of course, the randomness is true, but the output is not usually uniform. They are biased. So QRNG must follow by a post-processing, also we call whitening algorithm. So VQR for true uniform random number generation, we want to leverage both PRNG and quantum property. So why this true random does matter? Of course, cryptography, we need keys, total unpredictable, nonce. For example, for EEST encryption, we need this unpredictable nonce, sorts for IV. All this, we need a truly random. If the randomness is not truly, security can be collapsed, Of course, for machine learning, AI, Monte Carlo simulation, all this, the high quality of PRNG should be enough. But if you want to integrate with the cryptographic, then you need a true randomness. So real world failures, once the true random is broken, basically predictable, then the security is becoming trouble. So our goal is trying to get reliable, auditable, high entropy randomness and community system with all our system. This is big challenge. I should say, I never expect this before January 2025. I think this is impossible. So after New Year, I explore this entropy through the computer system. We found this actually magic things. So basically, we call QPP RNG is leverage both PRNG and QRNG. We want to put them together. So that is basically, you can say visually, visual quantum random reality or randomness. So in order for us to talk about this QPP RNG, we did go back a little bit to 7-8 years ago. You know, this I think this perfect secrecy from Shannon, which published in 1948, and we know the OTP is perfect, but you can only use for one time. So the problem, why? How can we make perfect secrecy reusable? This struck me for almost 2 decades, until 2027, when I visit my, childhood village. I figure out this, OTP is based on the Boolean algebra computing, and now quantum computing is a linear algebra. So the shift from Boolean to linear actually is from number, for n-bit system numbers, the state is 2 power of n, to n-bit system quantum system, that's the 2 power of n basis, basis vector. So then you have a big jump from 2 power of n possible operation to 2 power of n factorial this many operation. That's what we call QPP. Briefly, what is a QPP? QPP is basically permutation cryptographic primitives with a 2 power of n factorial possible key or gates. The gates, like what Solomon said, this operation, but for n-bit or n-qubit system, how many this permutation gates is? 2 power of n factorial. This is well known since almost 200 years ago from Galois. So the problem is how we can use that, So after we understand this QPP can be used for cryptography, so then we extend this QPP for symmetric crypto, like OTP style, AES-like block stream cipher. Then, of course, this implementation, you can go matrix implementation for classical system. You can go GITS implementation in quantum native, like Alain already did this implementation in IBM quantum computing system. So also the permutation gates can be implemented arithmetically, mathematically. So that's where we created this public key, HPP key, homomorphic polynomial public key, which can be quantum safe for KEM, K in computation mechanism, and digital signature. So this year we accidentally found this can be extended for random number generation. So that means, crypto, we found this QPP to be a DNA for cryptography. Here is a simple model, We always know array, order array, for example, 1 to number n. We have the how many permutation for this order array? You have a permutation n factorial. For example, if n equal to 4, you have 4 factorial, you have 24 permutation. If n equal to 5, you have 120 permutation. If n equal to 6, 720 permutation. So permutation space is always n factorial. The beauty is that this order array, array C, can be considered as a cyber array of order array AI through a permutation P, the P hat. So, and also we know all the permutation or gates or operators, they are unitary reversible, and it can be use a set of permutation to represent another permutation. This is where we create this random quantum permutation path P inverse equal to this product, all this. So this basically you can randomly generate this permutation operation, then make this path to be a reverse permutation of P, so you can go to sort the system. So we knew this. Actually, we knew this for long time, but we thought this is stupid sorting algorithm. But stupid means entropy. So here we can we create this, so we can repeat for sorting m time, so that we have the possibility m time n factorial become this entropy source. So this is this system that will offer you entropy equal to log base 2 m time n factorial. If you want to create an n-bit entropy source, you needed this log to be much larger than n. Here is the table giving you for n capital N equal to 4, then m from 1 to 4. You can see the equivalent entropy equal to from 4.58 to 6.58 bits. Okay. So a high-level view for this, a VQR system for one number generation, it consists of a permutation sorting engine, a computing system as entropy source. The two conjugated observables in the system is how many permutations used to sort this disorder array, and how much time it's taken to complete it. Of course, n we can consider as an operator, permutation count, okay, to complete a certain sorting cycle. Then we can reduce use the mode 2 power of n to produce the number in the n-bit system. Time, this ellipse sorting time, this is a magic for any computer system. For a given disorder array, then you try to use the same sorting path, QPV path, the time every time is different. Unbelievably, they're different. Okay, so this creates this N operator and T operator. They are conjugate of observables. You never be predicted this two the T. So here's a diagram to show how this QPP origin design make it work. So the system will output n, the permutation count, or modulo 2 power of n, or the permutation time modulo 2 power of n. So to be the evidence for true uniform randomness number generation, you need to have these 3 items. First, the uniform output for each number from 0 to 2 power of n minus 1 should be appear to a theoretical identical probability. In practice, they're not exactly the same, but they have a fluctuation. Then the normal distribution, the frequency of the symbol over many trial, or the symbol count cluster around the mean. So you can see the diagram at the bottom. The left side they will show averagely they are around the average, so they have fluctuation. Then the fluctuation, the count, if you do this bell, this called bell graph, you will see a normal distribution. So then there's a theorem called central limit theorem. If this is a distribution, normalized distribution for the sample count following the standard normal distribution, then this each symbol's distribution is uniform. We will see this later on. So this is a diagram I did the calculation, did this sorting with the 4 elements. The disorder is 3, 0, 1, 2. So we're trying to sort it back to 0, 1, 2, 3. So you can see here, this is for 1 million times sorting. 1 million times sorting, with each sorting we repeat it 4 times. So so this you can see on the left-hand side, the permutation count distribution is skewed, right skewed distribution with a long tails. They are not uniformly. At the bottom, left bottom is the time taken is also similar right skewed distribution with a long tail. However, if we do the projection to computational base for n bits computational base, you can find that they are become some certain uniform distribution. So for this, we take this, consider this as 4 bits random number generation. So you can see they produce this from 0 to 15, 16 samples. Each sample accumulated almost 32,000 times. So this make up mean, So you can see top and bottom on the right-hand side, we call this reduced distribution, looks almost uniform. So here I can show you on a certain principle we discovered, in this system. For a given quantum permutation path, QBP path 1 to 10, for each given path, we repeat many times. Here at least 10 times. You can see the permutation count is the same, but the permutation time always changing. Always changing. That is the beauty. We never saw this in the classical system. So here we want to show you how this system converging to a uniform distribution. With n 4 elements array, repetition time m lowercase m equal to 1. You can see this Bayer graph. They have a standard deviation sigma over 1,000 for the n. And on the right-hand side for the time t, over 2,000. So there's a lot normal distribution because the sigma is too large. If we increase for the same given disorder array, increase the repetition time to 2, the squeeze condensed to the central position. For averagely speaking, there are 3,900 frequency. On the left-hand side, the standard deviation reduced to 115. On the right-hand side, for the time, they reduced to 3,080. The standard deviation. Once we continue, we increase the repetition m to 3. On the right-hand side, for the permutation count, you see this the standard deviation, reduced to 64.3, and on the right-hand side, reduced to 72. They're almost close to the standard deviation, standard distribution. Let's further we get the m equal to 4. Both time, sorting time and sorting permutation count, they coincidentally going to converge standard distribution. Once this becomes a standard distribution, then the sample value from 0 to 15 become uniform. Okay, that is a central limit theorem. So here is a table to show you what's the standardization, standard deviation for the top part of this table. You can see when n from 1 to 4, the standard deviation is going downstream to the theoretical one. Theoretical should be 62.38. They're very close, very close. And to prove your random number generation to be, truly identical independent device IID, that's at least the standard. You also needed to measure the entropy and the chi-square, the very critical chi-square. So you can say for 8 bits, when m equal to 1, you see the entropy is 7.9. Then m equal to 2, they raise to 7.9993. And for same thing for n, for the permutation count and for permutation time. And chi-square, the ideal theoretical value is 255, but the practical will continue to close to 255. So this is a experiment to show, to demonstrate this QPP RNG converging to uniform predictable random generation. So once we prove that, so we can now merge this two distribution to one. So using the PRNG to generate permutation path. However, the PRNG will be driven by the system jitter, system jitter, the permutation time. So now they can uniformly generates the random number output the delta n. So we recently published a paper in the scientific reports, reports across all of this major platform: Mac OS M1, Mac OS Intel, Windows 11 with Intel, and Raspberry Pi. They show almost similar, pass the least standardization requirement for the minimum entropy. We reach sample A7. Compared with the commercial RNG like ID Quantis, the most popular one, Quantis. So our minimum entropy is almost identical with this QRNG. However, we achieve this in the normal, ordinary computing system. So one more thing is we have did this benchmark for mobile, iOS, and Android, demonstrate similar behavior. So we can enable all this computing device to be truly uniform random generator without require extra spatial hardware. And we also did this in the IoT device ST Micro. Of course, that's slower, but has similar behavior. So in conclusion, virtual quantum reality for truly uniform random generator offer programmatic auditable path to true uniform randomness on any computing system. So this QPP RNG demonstrates how quantum inspired solution plus system physical jitter, because all this integrated jitters across the system architecture and the operating system, scheduling, everything integrated together, produce high quality entropy. So anybody if want to try this, we can discuss after the this session, or you can reach me send my email. You can get contact me from my LinkedIn. We can have a more discussion. Thanks very much. This is my presentation.
Thanks very much, Dr. Randy. So it's a very excellent talk and a very excellent presentation indeed. And thanks for highlighting the role of virtual quantum reality and also the awesome portability of quantum permutation pad with random number generator, and also how this is really portable on different hardware. So the question now, are you gonna, for example, do you have a vision to like commercialize this as a product or as a software, or what do you envision?
Thank you very much. You know, of course, we already implemented this in our product. So basically, we already made a demonstration over this ST Micro seminar. Because this, you know, we're looking for this unpredictable, so without extra cost. So this is very interesting. You know, think about it. Probably 1 more minute I talk about, you know, so for in the past century we look for the cryptography. The cryptography itself is open. You always have the, you know, symmetric like AES rely on this unpredictable true random key. Then where you get this key, use public key to distribute this. The public key is broken, then you have to create a PQC system. Then once we face the PQC cryptography, we forgot where we get the true random. So that's how, okay, we need the QRNG, we need TRNG. Think about how you integrate this QRNG, TRNG into your cell phone, into your system. This have a scalability. Basically, from piece to piece, they're opened. So cryptography, they have 3 pillars: symmetric encryption, public key, a random number. These 3, there are a lot of complete system, like an ecosystem. Every broken piece, like if you use a Kyber, all the random numbers PRNG. Okay, if you do QRNG, now we have trouble how to put the QRNG with Kyber. You cannot, basically. This is a problem. The system broken. So whenever system broken, there is a weakness of the system security, right? So we try to create a ecosystem. We build this into the public key, then into the symmetric key. So they kind of self-closed system. I think this is important.
Yeah, definitely. Yeah, thanks for for this impressive. I'm pretty sure it's like an impressive product, and also we'll be looking forward to try and also test it in the near future.
Yeah.
So thanks very much, Randy. And now we are gonna move to the actual use case of the quantum permutation pad on real quantum hardware. And I'm just sharing my next my screen. Yeah, so I can present our next speaker. Our next speaker is Alain Chancey. Mr. And I will introduce quantum permutation pad QPP demos from noiseless simulation to running on a real CPU.
Thank you for having me yet again. I've made a couple of presentations of QPP. My background, I mean, you can look up my LinkedIn profile, but basically I'm a co-author of a book, Quantum Chemistry and Computing for the Curious. I'm also president of Molket SAS, co-founded with Taha. Molket is a member of QEDC and QUIC. I'm a Qiskit advocate. recently might have seen my post. I've accepted the invitation to attend the 2025 Quantum Developer Conference by IBM, which is an honor. But also, I've been a speaker at the IEEE 14th International Conference on Communications, Circuits and Systems, ICCCAS for short, in Wuhan, China, remotely, earlier this year. It was not the first time, actually, I was invited. And thank you, by the way, Andy, for sponsoring my presentation. So so on the right-hand side, you see the cover of the publication, and on the left-hand side, the certificate of achievement for this year. So since Randy covered on his, I mean, basically my work is more an implementation, an evolution of a toy model, which was put as an illustration to a paper co-written by Randy Kuang and Maria Perepesha and co. And this is the paper was backed in October of 2022. And the illustration was written in Qiskit, so I couldn't resist the temptation of running it. And the first time I ran it, it took about 2 hours on my powerful laptop to just run to completion the simulated exchange of a fairly small image. And at the time, it was back in late 2022. It was almost it was not realistic to run this on an actual quantum processing unit, but it was very interesting from a theoretical standpoint. So ever since, I've added some bells and whistles, and today I'm going to present that to you. And there will be it's the good news is that it's available on. So I guess you can see my screen. Yep, it's available on GitHub. Actually, there are 2 repos. One QPP -Alain, another one QPP-Alain real QPUs, where I put the experiments with real QPUs. So basically, it's fairly well documented. You can see there are 3 different experiments I have published here. That was 2 qubits, 4 qubits, 9 qubits, and it's very well documented. And this is what we are going to follow, actually. So I'm going to share this is live demo, right? So this is Jupyter Notebook. This is the one which represents Bob. Bob as a UVCon server. So I started it a while ago, but I can do it again just to show you that it's a real demo, right? So it's I guess most of you must be familiar with Jupyter Notebooks. I find it very convenient because it combines neat documentation, LaTeX formulas for mathematical formulas, quantum Dirac notation, text. It could even embed videos, but of course it runs code. So the Bob agent has been started. It's actually one of the components which I use in my other work for agent-to-agent communication for AI. And on the left-hand side, you can see, and again, I can start it again just to show you that it's a real presentation live. So actually, there is just one Python, but the advantage of doing it in Jupyter Notebook is that we get more stuff. So I've started the so-called Gradio user interface, which is a very convenient tool. It's written in pure Python. And you can see there, I can configure and run a quantum permutation path simulation. So this is what we're going to do. A number of qubits, that's 2. Let's see, or I use already this image, a fairly large image of the Mont Saint-Michel in France. For the first time, I will use Air Simulator Noiseless, which is a very efficient simulator provided by, I think it's within the IBM quantum community. The version, this is where it's interesting, I'd say, because the original qubit permutation pad was, but I will explain later. Okay, trace just to see what's going on. Simulation. There is a purely classical simulation with matrix multiplication, but it's not what I'm going to show you. And the so-called simulation 1, this choice is for actual quantum processing unit or air simulator. So I will just say the configuration there. Okay. Okay, and then I go back to this. Okay, this configuration with Gradio is complete. Type run simulation. So this is where the fun begins, right? And then we have got a trace, and so we see all the parameters. And this is where you see this is the advantage of using Jupyter Notebook as opposed to plain vanilla Python. So you can see the first permutation. So a permutation pad, by definition, has a bunch of permutations. Oops, well, yeah, it's so fast. It has already completed. I've got to go up to show you again. Okay, so what happens is that there are a number of permutations in a pad. So you can see it, for those of you who might not be familiar with this kind of drawing. So this means that there are 2 qubits, Q0, Q1. C, this is for the measurement. This is the barrier, don't worry. And there is one line and it's like a black box nowadays. You don't see much. And basically this unitary, it's a Hamiltonian. It represents an operator, a quantum operator. It faithfully implements this, and with only 2 qubits, right? And so there are a bunch of permutations, and for each permutations, the program computes all the possible inputs. So for 2 qubits, we have got 2 to the power 2. We have got 4 possible combinations of inputs, which are represented there. 0, 0, 1, 0, in binary, 0, 1, and 1, 1. Okay, and we go all the way down. Okay, and then where do we see? Okay, sorry. I hope you see well. So going to scroll down. So there are a bunch of permutations with 2 qubits. I think there's 56 permutations. I mean, the number of permutations was documented. There was a table, still there, by the way, in the original article by Randy Korn and Maria Perpeshenko that gave the suggested number, recommended number of permutations. So there are 56, if we include 0 permutations in the pad. So it has done all the work, and then it has, you see, the encryption, the time it took for the encryption is very, very slow. I can save the work. I've got to save the notebook first because this cannot be done. And then, up, and it is saved. And now I can go to Bob's side. So Bob, and there is a simpler Jupyter Notebook. Okay, I start. Let's make sure we start afresh. I hope you can see the demo. Huh? And then, this is where it's fun. There is the choice between version 0 and version 1, and you will see what it means. I will choose version 1 this time. And you see, you're about to see. Okay, so this time it's different. So this is something kind of a surprise because there is a theorem which proves that it is impossible to implement such a permutation, which just swaps. And this is, oops, it has ended. So I've got, it's so fast nowadays. I've got to scroll up to let you see. So it's the same number of permutations on Bob's side. So Alice has encrypted the message, has sent it via the RPC protocol, and now Bob is using the inverse matrices to decrypt. So you see, for example, just to show you the first one, it's worth realizing this. It all makes sense, right, when you see it. I think it's more. Well, there's a bunch of them, but we're getting there. Yep. When you see permutation 0, this side, and look on this side, it's the conjugate transpose, because there is only 0, 1. It's the transpose, but so this matrix, this operation, is exactly the what is needed to decipher, if you want, a piece of text which has been encrypted with this one. Okay, and so what I was saying, yes, there is a theorem which shows that for 2 qubits you cannot implement the 2 qubits permutation pad only with swap gates. And these are swap gates. However, I found out that if you accept to pay to have the cost of having not just 2 qubits but 2 to the power of 2, then you can do it only with swaps. And this is interesting because the depth of the quantum circuit is much much lower, and of course at the end you will say, but does it work? Yeah, I mean, you can see there. I should have showed the original image, but yes, at the end we do get the image decrypted without a degradation. So that is fun. I think so. This was a simulation, noiseless. So okay, I would say, well, it's no big deal. But something I won't show you live, which I achieved recently, was to do a simulation. A simulation with air simulator, but this time with a noise model from a real quantum processing unit. And this time it's more ambitious because I've got, it's 4 qubits, but with the choice of having swap gates, so it's actually 16 qubits. So it starts to be on a laptop, on my laptop, which only has 32 qubits, 32 gigabytes memory available in Ubuntu out of 64 gigabytes. The maximum in practice I can run in terms of simulation with air simulator is around 22 qubits. Beyond that, it consumes too much memory. So 16 qubits is about the biggest, because next one is 2 to the power 5, which is 32. I can no longer simulate this on my laptop. And so, so Alice has chosen this way of doing it, and it uses the air simulator. I hope you can read, otherwise I read it for you, with method state vector, because there are several ways of simulating quantum circuit. One which is a state vector, there is another one which is called matrix product state, and a noise model from Factorino. So that's interesting because, and you can see there, instead of this, for example, I can put I could put fake Torino, for example, which is the name for those of you who are familiar with the IBM quantum platform. Torino and Brisbane are the only two at the moment available for those who have the free plan, like me. And so Factorino, it's as its name implies, it's something which is a nice feature provided by Qiskit, more precisely the IBM Qiskit runtime environment. You can simulate what's going on, so it's very convenient. So what I've done here, whoops, where was I? Oh yeah, I was there. So simply by selecting Factorino in the interface, the program has automatically built what is needed to run a simulation with a noise model. So it takes a while. It takes about 1 minute on my rather powerful laptop to simulate 16 qubits, but with a noise model. So it starts to be interesting. So there are less many permutations in the pad because because we don't need to have that many permutations compared to 2 qubits. And so it took about 6 minutes 30 seconds to basically compute all the possible outputs for all the possible inputs for each permutation in the pad. And then this is stored in a, guess what, Python dictionary. And then the encryption goes real fast. And then if we look at what's going on Bob's side, so sorry, I've got to go up again. So where are we? Oh yeah, we are in the, sorry. Yep, I'm going to go, and this is available, this is online. I mean, it's a public repo, so you can have a look at it. So I'm going to see what's going on Bob's side. And well, it's symmetric, so nothing really fancy. So it's symmetric. But of course, what's important is a decrypted. Yes, it is good. It's not corrupted. So I demonstrated the noiseless. The well, you have got to trust me. It's archived on GitHub. The simulation with noise model. And now, guess what? A couple of days ago, I managed to do a simulation on a real QPU, real one. So I'm going to show you.
Oh.
And so, of course, credit, and of course, this is okay. This is my stuff is provided with the MIT license, and I have, you know, complying with all the rules associated with the articles by analysts. All this, okay. So I did. This is 3 qubits, but the version with swap, so it's actually 8 qubits, and you see. This is the evidence. There were 1, 2, 3, 4, 5, 6, 7, 8 jobs in succession. Why 8? Because I basically compute for each permutation. So this is the quantum circuit which represents a permutation. I compute all the possible combinations, but since it is with swap gates, there are only 8 combinations. Remember, it's 3 qubits, so 2 to the power 3 is 8. There are only 8 possible combinations, but that means running each this circuit 8 times, and this is what we see here. And so the outcome is there. And I limited the because yeah, it took about 45 seconds to run, but I only have 10 minutes QPU usage on my free plan. So and I've reached the maximum actually, so I cannot do it again. And on Bob's side, so let's see on Bob's side what's going on. So Bob did the same. So actually, yeah, also on a real QPU. This was the least busy device. It's called IBM Westbound. It's a real QPU, and again 8 jobs on, and that's it. And of course, the most important thing. Yep, the image is there, despite the fact I'm running on a noisy quantum processing unit with no error correction. So that's in my opinion, that's impressive because, and guess what? I wish I could do more, but I've used up all the, you know. I've got to wait a couple of days for August because I've used up all the remaining time 0. So, but next time what I will do, and I will keep you updated, or I will post something about it, is I would like to do, you know, 4 qubits with the to the power of 4, which is 16, on not a factor, but if I put none, it will pick the least busy device, or I can explicitly mention, because the biggest, I mean, the most powerful or the highest quality machine available in the free plan is IBM Torino. It's got 133 qubits, and you can have access to it in free plan. So with this interface, I mean, you're free, and I welcome the idea of you downloading the stuff from my repo and install. You might have to install a few things, but it's well documented in my Jupyter notebooks. And then with this easy interface. So when you do when you do on a real QPU, in order to avoid consuming all the credit you have, you can limit the number of permutations. And you can do things as well. This is when you do on a real QPU, and you can either do it like I've done, which is from a Jupyter notebook, and you limit this to the configuring the parameters, but you can also run a full simulation. Okay. So so that's what I wanted to share with you. I don't know, Taha, how am I doing with time? If you wish, I
Yeah,
can.
it's fine. Yeah. That's if you can just show them the GitHub repo again, because some of them
Yes,
wanted to use it.
yeah.
So question in the chat.
So this is the GitHub repo, QPP dash, and there is the sister one, which I've designed because I plan to make some other experiments. So I might actually recreate this one, but this one should be fairly stable. And all you have to do basically, you have to download the content of Alice. It's download all of this stuff, and it's got a few images, but you can of course use your own. There is a Christmas tree, and there is the hello text, and also you need to download all the content of the Bob. So you see the Bob agent, and okay, and don't worry about this. This is done automatically. It's a JSON file, so the configuration is automatically saved there, and so that's it. And of course, I can be reached on the Qiskit Discord. I'm of course obviously visible. So if you have got because this is a something I'm proud of for the for showing off with fellow Qiskit advocates and others. In a nutshell, my work is more the purpose is not really to put this into production. It's really, I think, a very nice use case for benchmarking and for testing how to do from how to work from simulating with air simulator noiseless, and then move on to simulation with a noise model from a real quantum processing unit. And when you are confident, this is the case for me. I mean, I honestly believe that with 4 qubits, it should work. So my next attempt on a real qubit QPU will be to run this, which I successfully ran with simulation with a noise model, to run this on a real QPU. And I think 16 jobs. Hopefully, that should fit within 10 minutes easily. So this is the experiment I'm going to do. But of course, if you guys you have a free plan, you have plenty of time to spend. Maybe it's a good idea actually, just a couple of days before the resetting. So you could burn some minutes with my stuff, and you could leapfrog me and say, Alain, yeah, we managed to run on a real QPU with your stuff. It works. It's not guaranteed to work again because the depth starts to be a bit longer. Now it looks like it's one operation, a swap gate. Yes, it is in theory, but in practice it is implemented with 3 CNOTs. So at least on the IBM quantum devices. So the number of the depths, the number of gates. So you take the number 1, 2, 3. Well, it says so you've got to multiply by 3. So it's 12. And CNOTs are tough, right? It's Don Clifford, I think. So depth 12, no error correction. Will it work? I don't know. that's the excitement of running this. And then if it works, then next step is to try with 32 qubits. I mean 5 QPP 5 qubit, but version with one with swaps, which is 32 qubits, and that beyond what can be simulated with air simulator. At least not on on a laptop, maybe on a workstation, who knows? And then if it works, the next step is to go, because with 133 qubits, you know, it's easy to make a computation with 5, you have 32, 6, 64, 7, so 128. So yeah, that could be worth attempting. QPP 7 qubits version 1, which is swaps, which would use up 128 qubits. Okay, if it works, that would be, I think it would be an achievement. Again, no error correction. Huh? Okay, so I'm open to, I will keep sharing, but I'm open to questions if you have got questions.
So thanks very much, Alain, for this nice and outstanding work that you have done with QPP and all of this nice benchmarking and the testing and everything. It's very helpful and enlightful as well to see this and also have all of this benchmarking. Okay, so it's a time for questions. Please put your question in the chat if you have one. And in the meantime, until they share their questions. Okay, someone is writing. So in your perspective, what could be the extrapolation of the number of qubits? So for example, would it work was larger than 8 qubits on 12, like 12 qubits, 16, or do you have like something constrained with the coupling map of the qubits? What's your perspective on this?
Well, that's a very good question. By the way, the coupling map and that kind of concern is also is maybe more relevant for the other great work I've done, which is the SQD, sample-based quantum diagonalization, which, by the way, I will present during the
Hackathon, yes.
hackathon.
The hackathon next week. Yes, yeah.
Next week.
Next
But
week.
for this, it's the advantage. It's fairly easy. First of all, it's easy to simulate classically with matrix multiplication, and you can do this. But again, I mean, this is also based on a toy model, which illustrated the paper by Randy. I would not claim that this could be the complete implementation that Randy had in mind originally. There might be more features, but the point is, I don't know, and this is where the advantage, because the way, of course, I've implemented this in my implementation, there is no name hard coded. So if there is IBM underscore what's it, which is available next year, you should be able to test it with this. With my code, with now not a single line of code changed, right? And so I'd say it could be used for benchmarking purposes, but also not just with IBM quantum devices. Any quantum system that can be made to work with Qiskit code as input, that could be used. So the answer to the question, I don't know. There is no practical limit. I mean, if one day, I mean, hopefully in a couple of days, by 2029, we should have quantum devices with thousands of qubits, error corrected. So yep, we shall see. But this is in my opinion a great tool to benchmark. Imagine the progress. Okay, to end of 2022, it was impossible. I think it was impossible to run on an actual QPU because of the noise, the noisy qubits. And a couple of years later, it becomes possible, and for free, which is amazing, because the machine IBM Torino, for example, 133 qubits is made available to the public with the free plan, and it is much more powerful than the one which was used for research last year in 2024. I think about the work around the sample-based quantum diagonalization (SQD). So, so my question is, yeah, I don't know. I mean, but we will be interested to find out.
Yeah. So thanks very much, Alain. Thanks for showing this nice also work, which is very helpful for benchmarking and presumably also different types of hardware and also the different number of qubits. So we have another question from Jan Blomart. And Jan asks, would mid-circuit measurement be a way to reduce the depth and still run better programs? Does this make sense at all to consider?
I would say not for this particular, not for the QPP, because again it's so simple. It's a bunch of especially the version which uses only swap gates. However, the mid-circuit measurement feature is definitely very, very useful. It's a game changer for protocols. I think about in particular for quantum phase estimation, QPE, which is a promising algorithm, but at the moment we don't have the machines with the capability. And with mid-circuit measurement, quantum phase estimation can be implemented with fewer qubits, but at the expense of having more longer depth. But in this case, it's just. But that's the beauty of it. It's just very simple. Okay. So thank you, Jan. But no, for this case, I don't think mid-circuit measurement would make a difference. But it would be very relevant for the topic I will present during the Alexandria Hackathon, i.e. the SQD.
Alain, just a couple of comments here. Yeah, so Alain actually, who is the very pioneer to implement QPP, use this smart way to in a noise system or simulation system. We did the real implementation for 2 qubits in the IBM 5 qubit system. So indeed, in there we simply use their combination to produce the circuit. So anything beyond three qubits permutation gates, the depth is way beyond the beyond this noise system to handle and make a meaningful results. So this way, they implement, you can get a very simple implementation. And I also noticed some other research proposed to use other smart way to avoid this direct combinations of the system. So that can also make the depth shorter. You know, once you use the very basic system combination, they produce a huge depths. You know. Make us trouble.
Yes.
And I think
thank you, Andy. Yeah.
So if somebody interested, actually you can perform this quantum computing to classical computing communication. You can implement the same way, you know, in classical system using matrix. So then you can communicate between these two systems. This can be mimicking, you know, largely what our communication system, you know, when sitting in front of your computer, you never be aware behind your computer there's different interface from using different media to transmit data. So in the future, the quantum computing will be similar. You know, you have a quantum processor interface, so they can do this convert to the data, and so they can make this hybrid system. Quantum secure communication from classical to quantum, from quantum to quantum, and from quantum to classical. So that's a hybrid quantum secure system will be the future of the real world's quantum secure communication. You cannot imagine pure quantum to quantum over the internet. I think that is probably far away from reality. So again, I appreciate Alan to make such a great effort to implement this in the real system. That is a beauty.
Yeah, thank you, Randy. And I would say, yeah, quite rightly, the reason why I use the version so-called V1 with only swap gates is because the depth is much shorter. But for the 9 qubits implementation, which are simulated noiseless, okay. At one stage, I was the number of the depth was something like 60,000 gates. 60,000 gates, way beyond what the best quantum machine can achieve. So the implementation, the original implementation, which doesn't use swap gates, it's very challenging to make it work on a real QPU. I'm not even sure that the 3 qubits V0 implementation would have run successfully on IBM Torino. So that's very important. But that's the advantage of my implementation. You can try one or the other and try it out. But thank you, Andy. And there is indeed yeah, it shows also it's possible to mix purely classical matrix multiplication based and quantum, and it's also quantum inspired. Well, thank you, Andy, for your great support.
So yeah, thanks very much, Alain, for your nice presentation and the nice work, and thanks, Randy, for your comments and also this nice discussion. So we are gonna now move to the next speaker. So it will be now me to talk about different topics, not entirely different, but just with a different focus on quantum chemistry and the quantum computing, with a conceptual use case that could be used for cybersecurity. Okay, so still see my screen? Okay, do you see this, the shared screen or not yet?
Yeah.
Yeah. Okay, so
yeah, now we see your screen.
Yeah, thanks, Randy. So currently I'm the general manager of Molkit SAS. I'm also lecturer and researcher, quantum education officer at Amsterdam University of Applied Sciences in the Netherlands. Recently, we have co-developed a new master where I co-developed it with other team members from different universities. It's a new joint degree in applied quantum technology, and it's a professional master made to prepare the future workforce for the quantum industry. This master is going to start actually in 2 weeks from now. The first introductory weeks is going to start next week with the hackathon. So after the hackathon in Alexandria, when I'm back to the Netherlands, we are going to have also our introductory week for the master. And we have a very nice number of students who joined the master. I also have a research profile, which now I try to focus on quantum machine learning, physics-inspired AI for chemistry and materials. And I hold the PhD in quantum theoretical chemistry, and I'm a YouTuber. Feel free to check my YouTube channels. I have two, one in Arabic and one in English. Okay, I'm now gonna share the presentation. Okay, so hopefully now you are seeing my presentation. Okay, so I'm gonna talk now about quantum molecular dynamics and of molecules in space And this is like the quantum chemistry and the computing, the eternal walls. Okay, so this talk will cover three things. Of course, I'm going to highlight them quickly for the sake of time, but I wanted to give you a flavor about what quantum molecular dynamics is doing, how it's helpful for quantum computing, and how quantum computing could be of a good help or offers a good help to quantum molecular dynamics. And of course, what we are doing in research and what we are doing also at Molkit. Also feel free to contact us for collaboration. So the part that I'm going to share in quantum molecular dynamics is part of my PhD thesis, which is published and completed in 2024. And please feel free to check out these papers for more technical knowledge. Okay, so for the first work, during the PhD, we used quantum molecular dynamics to interpret or model the spectra received by James Webb Space Telescope. There is quest to understand the chemical compositions of interstellar media. And of course, it's very hard to send a person to bring a sample from these distant clouds. So the only way is to bring like some information via light. So the light carries information about this, not only like information about the physics or the thermodynamics, but also even the fingerprints of dominant molecules in such interstellar media. This is a depicted image of the light that has been produced by these distant objects and then collected by the mirror and the detectors of the International James Webb Space Telescope. This is one of the most advanced telescopes and even surpassing Hubble Space Telescope, which is about to retire in the near future. And then with the good modeling, you can interpret and knows how much carbon, how much nitrogen, and how much oxygen are really present in such media. Okay, so still a close look on James Webb, and James Webb has powerful near and mid-infrared observational capabilities. So it is used to detect the rotational and the vibrational transitions that happens in the molecule species in interstellar media, and then resolve them accurately. This is an example of what typical spectra we receive, or it's recorded the spectra by the detector. So if the modeling is done right, you can extract and decipher the spectra to extract useful data. And of course, next to identifying the peaks where the molecules or certain transitions in these molecules happen, you can also gather information about the local temperature, molecular abundances, and of course, other more information. So why this PhD was about this? Because there was like a key to, or the quest to understand the chemical composition of the formation of the clouds that are responsible for the formation of planets. And those clouds come from the collapse of gigantic nebula. Those nebula are very gigantic molecular clouds that are space, which are collapsing by the act of gravity until the core is hot and dense enough, and then a new star is born. So there's like a new sun in the middle. And then due to the conservation of angular momentum, the whole system starts to spin very, very fast. It's like having a very fast spinning cosmic pizza. And they start to flatten, where the planets start to form, like you have the olives on pizza in their own shape. And then the question is, okay, can we understand and model such a process? So to answer this, we need to understand more, or to know the composition, at least for key molecules like carbon monoxide, carbon dioxide, hydrogen cyanide, water, acetylene, and methane. This is still also the same example. You have plenty of these protoplanetary disks, those clouds that are very flat, where planets are formed inside or from. And then that's the spectra, typical spectra you receive. And then if you have the enough information, or you have the enough numbers to create a theoretical model to simulate the spectra, you can assign the peaks easily. So here we have a successful story where the theoretical molecular astronomers could get the numbers from us and from other groups as well around the world who are computing, make quantum mechanical simulations. And then if they do that, they can assign the peaks to the transition. So they see, oh yeah, this peak is, for example, for the isotope of carbon dioxide. This transition is for water. This is for a certain vibration mode in carbon dioxide. This is for hydrogen cyanide, and so on. So how the light is produced, it comes to the James Webb Space Telescope. The light is produced via two main processes. The first one is the collisional processes, where the molecules start to hit one another or collide with one another, and then they cause de-excitation, and then you get photons. Or biradiative processes also, where the photons can excite the molecule, and the molecule can de-excite by spontaneous emission. Then after some time, it relaxes naturally and emit light, or by stimulated emission. Each part of this process is described by a coefficient. This coefficient represents the efficiency of this part. So we have now the collision rate coefficient. This represents the efficiency of this process to happen, of excitation and de-excitation in the collision. If we have these two energy level system, we have like a ground state and one excited state. And Einstein coefficients, which is represent the efficiency of going from ground to excited state by radiative excitation, or vice versa, from higher to lower via stimulated or spontaneous emission. Of course, these numbers for small molecules are known, those Einstein coefficients. However, for collision rates, they aren't available in the literature, not for all the small molecules, and those are computed accurately from quantum mechanical calculations and the full quantum simulations. Okay, so we were interested in doing, for example, the CO2, because CO2 is available in different places in solar system, but also in exoplanets and interstellar media. And we used quantum molecular dynamics to simulate this. And what is quantum molecular dynamics? From its name, it contains quantum and the molecular dynamics. So there is some dynamics of molecules. So this branch particularly combines quantum chemistry, which is the quantum mechanical treatments of electrons, and the molecular dynamics, which is the classical mechanical treatments of nuclei. If you blend these together, you get quantum molecular dynamics, which is the quantum mechanical treatments of both electrons and nuclei. Quantum molecular dynamics have very powerful applications, and it's also part of my research and part of also MolKit offerings, and that provide modeling and the basis for many applications like quantum sensing, molecular qubits, chemical reactions, chemical evolution, molecular collisions, quantum control, and even quantum memory and quantum computing. Most of the studies for semi-lattice lattices and things related to ultra cold atoms and the neutral atoms are coming from models based on quantum molecular dynamics, which help a lot in understanding the interactions and the coupling between these virtual qubits. Okay, so we're back to the focus. The focus was on CO2 and carbon dioxide. We can describe it quantum mechanical like this. The complexity about when we go to polyatomic molecules is that they, since they have more than two atoms, they can vibrate in different, in very specific, but also different configurations. It's called different vibrational modes. And for example, CO2 is a linear molecule. It has 3 atoms. So it has 4 vibrational modes. So like the symmetric and bend mode and asymmetric stretch. And the bend can happen in plane and out of the plane. And then you can imagine this as a rotation happening around the axis or the molecular axis of symmetry of the molecule. And for that, if we would like to describe this, we describe it with a kit. And that kit is labeling the quantum state. And the quantum state typically for rotational and vibrational state of a molecule of like CO2 is described by all vibrational modes, a quantum number that expresses the excitation of this mode. And then we have LV, which represents the vibrational angular momentum, these rotations, and then the rotation of the molecule around Z axis, for example. So if you wanted to do this on a computer, you would imagine that you need equations that has all of these quantum numbers or labeled by all of these quantum numbers. Now, if we look at one mode only, we can represent it with like a parabola or harmonic oscillator. And then the molecule could be in the ground, for example, in the ground state. And then once you hit it with something, it will go to the excited state and it can back again. So it can go up and down. And then this process, we would like to know the efficiency of it. And the simulation of this process can come from the quantum mechanical methods or the coupled channels method. And this method is very powerful because it simulates the typical collisions that's happening. Okay, as any physical system, we need a Hamiltonian to describe the system. This Hamiltonian should include the basic terms to describe this physical system. And in a typical Hamiltonian, we have a general term for kinetic energy and for the potential energy. And this expresses the dynamics of the total energy of the system. And this, since in our CO2, there is nuclear motion, there is vibration, where atoms can move together with reaching different amplitudes with the same frequency. And then it can have also rotations, would have an angular momentum and potential, how much they interact with one another. So there is interaction energy. And if we do this, if we describe this Hamiltonian and write correctly and mathematically, we can store it in a matrix. If we diagonalize this matrix and solve the eigenvalue equation, we get a spectra that represents the eigenstates of this system, and the state vectors will be the wave functions for every state. When CO2 comes to collide with another molecule like helium or like atom like helium or molecule like hydrogen molecule or anything, when they collide, we need also Hamiltonian to describe the state, and then we have the generic Hamiltonian. Any Hamiltonian, as I have indicated earlier, will contain kinetic energy part and also potential part. But then this is because it is a generic Hamiltonian, it also will include the individual Hamiltonian for the carbon dioxide. So the take-home message here is that you need a Hamiltonian to describe a system, and you need to accurately describe the terms involved in the Hamiltonian in order to get the proper wave functions and also the proper eigenstates. What makes this complicated is the way that you need to describe the Hamiltonian in a certain kernel or a certain space. We call it basis states. We have seen it with Randy Kyung when he was explaining the basis, also with Salim Higiz, where he explained the basis of the photon, the single photons, and the pulses could be represented as basis. And then similarly, the Hamiltonian should be for this system should be expressed in that way and be projected or expressed in terms of bases. This is the most difficult part sometimes in computational chemistry because you need to do a lot of theoretical work in order to get the expression of the Hamiltonian mathematically correct. Okay, so there is ingredients. So you have like the CO2 term. You can have also the potential, the interaction potential between the CO2 and the helium. And then if you have that, you can calculate the potential with some methods like CEST or any other quantum chemistry method. And if you do so, then you get your potential, you make a fit or interpolation. When you interpolate it, you have like a sort of an analytical representation of the potential. And if you do that, you can calculate the gradients, but also you can compute many points more than what you actually calculated with the quantum chemistry packages. Why we do that? Because quantum chemistry packages can be computationally expensive. And for that, you need to have a way to make an interpolation and also try to predict the points in between the points that you have already calculated. Then we get on a computer something like this. We label all these matrices with the quantum numbers. I'm not gonna go to the details of what these, but this is just a mental picture. To get it mentally, we have a matrix. This matrix is sort of expressed in a basis, and this basis is labeled by quantum numbers. And then we have, for example, here's a ground vibrational state. Here we have the first excited state, and then this like coupling that happens here in these off-diagonal elements, and those are really huge matrices. To give you an idea about that, you can have here a way of seeing this. If you have 100 equation to solve, it takes about half a second. If you have 300, you take about 4 seconds. If you have 60,000 equation, you take about 6,600 seconds. So clearly you see the time complexity, which goes with the number of coupled equations to power 3. And that's makes sometimes it's formidable and also computationally expensive to compute this for larger systems, or include even more vibration where you have many quantum numbers, and then your matrices will scale up and become much more expensive. Then we have reported few works from that. We have produced the packages, and those packages, after we did the theoretical work, we did the programming and coding of those packages, make them efficient to be suitable for high performance computing, and then compare the efficiencies or the cross sections with the experimental work. And here there is some light highlighting for what we do in the potential. So now we come, what quantum computing can do for quantum molecular dynamics. Obviously, we have seen the problem. We have a problem in the computational complexity of simulations. Once you apply those quantum simulations for larger system, the computational complexity will manifest itself, and it will be very complicated and very difficult to run the things, even with high performance computing and very advanced supercomputers, because you have this scalability behavior with a number of equations. So you need to do some tricks, do some approximations, some performs certain like a new theories like DFT, or trying to restrict the number of equations that you have to the most relevant part of your kernel or your domain, and so on. Okay, so now we see this computational complexity. It's not only in chemistry, but it's also happening in material design and the molecular design. And there is a promise from quantum computer to reduce this, which has been started in late 60s, but also in early 70s, and has been highlighted by Richard Feynman, that maybe we can compute the properties of molecules if we can recast this problem on and perform a computation on other molecules, and then we can go beyond the classical limits of classical computers. And as we have seen earlier, this is dependent on the definition of qubit, and the qubit can exist in a superposition between 0 and 1. This is an extra power than the classical bit, which only can have one unique state. However, when we measure the qubit, one state will remain and the other will disappear. Okay, so typically we work with quantum harmonic oscillators, and because this one, if you want to use quantum computing, you need a second quantization, and this actually comes from representing any potential, which we have seen earlier to describe the interaction between atoms, as harmonic, for example, oscillator, and then you can use what is called ladder operators to climb up or climb down. So this is called the second quantization, which means that you have something that's quantized, as a quantum system that's quantized, and then you can go up or down via these ladder operators. One operator will climb the step higher, and the other operator will take you down. And these are the expressions of these ladder operators. But using this clever method, you end up with a Hamiltonian, which is very unique. It only has two simple terms, A dagger A plus half times h power omega. This is a zoom in on the Hamiltonian. And then, of course, this Hamiltonian is more for harmonic. If you have anharmonicity, or you would like to have something realistic, then you need to add this anharmonic term and work with it. If we have the correct Hamiltonian, and which we have seen with this kinetic and the potential energy part, we need to express this Hamiltonian in terms of second quantization or ladder operators. And if we do so, we can use certain techniques to map this Hamiltonian into the qubit Hamiltonian. And there is something like Jordan-Wegrand transformation or using a V anharmonic and so on. And if you do that, you can just re-express the Hamiltonian in terms of qubit Hamiltonian, which is Hamiltonian that matches the type of the qubits and allows you to do performance and the computations on a particular hardware. Okay, so once this is done, this is a typical workflow for one of the common algorithms that's used now in quantum chemistry, regardless of whether it brings speed or accuracy or not. We are going to highlight this as we have the variational quantum eigensolver, and that's starts with the Hamiltonian representation, and then you need to encode your data to the Pauli operators, and then you group, and then you do the measurement, and the measurement will be done all at once. And this measurement will carry for you some information which you can use to update your parameters and do the computations again. Okay, so now what we are doing in Molkit at the moment. I have showed the PhD project, and then there was a part about my work in university. It's mainly about using quantum machine learning and quantum molecular dynamics in exploring further molecular species in space. We have collaboration now with Jan Blomert on this, and potentially Jan and I, we are going to collaborate on other projects or similar projects related to high energy physics or using quantum computing for high energy physics. Okay, now we come to Molkit. Molkit is a startup based in Paris, and we are providing and offers management consulting and AI services for quantum molecular dynamics, cryptography, and the neuromorphic-based computing. And we have worked actually very nice use cases, and we have an open source package available on GitHub. You are going to see the link at the end of the slides. And one of this is to use quantum chemical sensing for detecting the tampering in optical fibers. This coming from the slide owned by Molkit SAS. Of course, it's an open source, but if you want to use it, feel free to cite the slide of that. Okay, so what is the main idea of quantum chemical sensing? The main idea is that, okay, you can have an ultra cold gas, for example, connected to an optical fiber in a specific way, and that is detuned from the strength or the signal profile. And once a certain change will happen, it will make the molecule excite and de-excite, and we can detect that using our control part. And that will give an idea about that someone really wanted to hack as an optical fiber. It's not only about hacking, but also could be detected as natural effects or natural disasters, like the tectonic movement, plate movement in the beneath the surface of the Earth, which might impact the strength and also the quality of the optical fiber. Such devices can, of course, report about it. And also we propose to leverage AI to accelerate chemical design and quantum dynamic simulations. These AI applications can be trained on the inputs and outputs of quantum chemistry and dynamics algorithms, effectively replacing computationally expensive components. Furthermore, they can learn the scaling behavior of these algorithms, enabling extrapolation to larger system. And this is our open source package. Feel free to visit this. And there is a question I'm going to leave at the end. We can discuss it in the future monthly series before we forget it indeed. Could we have a generalized AI framework for all chemical simulations? Yeah, this is we are about to find out. Okay, so thanks. And if you have any question, please feel free to drop it in the chat. Okay, I see one comment from Santosh Barek. I'm deeply inspired by your, okay, I would like to be truly possible to collaborate and work with you. Of course, feel free to reach out to me on LinkedIn or reach out to us. And yeah, we can just explore and discuss ideas for sure. Okay, if there is no more questions, for the sake of time, we can move to our next speaker. And let me just remove the sharing the screen. And our next speaker is here, Mr. Greg Pitts. I'm just sharing my screen now. And Greg's gonna talk about quantum computing and the future of cybersecurity beyond the hype of QD. Okay, so Greg Pitts is the founder of AZ Quantum Computing, LLC, a cybersecurity and quantum computing consulting firm. Prior to that, he founded and ran Logos Solar LLC, a professional electrical engineering firm specializing in photovoltaic systems. After designing almost 400 PV plants, Underwriter Laboratories asked him to help formulate some of the photovoltaic standards in addition to devising photovoltaic system standards. He also wrote standards for wires, cables, breakers, and fuses that are in use in every building in the United States. He also wrote almost all the international standards for the GPV, for VW, Audi, Bentley in 2006. And also he was a test driver for VW, Audi, and Bentley in 2006, while in Silicon Valley in 1990s, he worked for Next, Apple, Symantec, Adobe, Virage, Netscape, and RSA. He volunteered at Compute Mentor, now at TechSoup Global, where computer experts donate their time to assist nonprofits. Greg is also a member of Mensa and the IEEE Quantum Security Framework Working Group. So welcome, Greg. I'm happy to host you, and please feel free to present your screen and share it. The floor is yours.
Super, thanks, Taha. How do I share my screen?
Yeah, you will find next to one smiley face, one button, one arrow that points up.
I don't have that. I've got this. Oh, there it is. 1 minute. Yeah. Okay. Thank you, Taha. I greatly appreciate you having me here. And I want to thank all of you there in the Middle East. I'm in Phoenix, Arizona, and I don't know if you saw the news, but 2 days ago we had a major dust storm, what all of you in the Middle East call a haboob, that set our standards since 2011. And I thought it was great fun to be out in. So anyway, I want to thank you all for sending that to me over here, so I get the feeling like I'm over there in the Middle East with you. Sorry.
Yeah, I said it could be a nice experience to try a bit of hot weather as well.
My estimated date on Q Day, hold on here, is 2030. And the reason for this is because in June, second week of June of this year, many companies announced their timeline on what they feel their production dates are going to be for the next 5 years or so, or 10 years actually, with many of them. IBM and Quantinuum in particular said they believe they're going to be able to have a quantum computer that will be able to, rough guesses, they didn't say it explicitly this way, but running the numbers with the number of the hardware they'll have, that they estimate around 2029, and another 6 or so companies estimated around 2030. So let's keep that in mind for a moment. So in any case, this will give us the number of qubits, qudits, qumons, depending on what technology we're talking about, that we are estimating will be able to factor the RSA 2048 encryption code. I'm going to use, whenever I say RSA 2048, I'm going to use that as shorthand because AES 256 and a few others are shortly behind that. And so when I'm saying RSA 2048, please think of the other ones as well. All right. There are 5 criteria that have to be met for a Q day. That is the day when quantum computers can factor RSA 2048. There are presently 83 quantum computer companies in the world, though I only think 3 will achieve that value, that manufacturing capability by 2030. Let's round up. Let's say it's 10 to make sure that we include, as far as I'm concerned, any possible outliers and so on and so forth. Also, let's consider that it takes 14 months to make a top-end computer. And so let's round that down to a year. Sorry, I messed up on this slide a little bit, but then the other thing is, another parameter to consider is that McKinsey estimated the time to crack an encrypted bit of RSA 2048 encryption with this type of computer will be almost 3 days. I believe they stated it would be 2.8 days. Let's round that figure down to 2.5 days. You can see what I'm doing by when I'm rounding these values to ensure that we have plenty of wiggle room as is required for any future prediction, because obviously we don't have crystal balls that are that good and so on and so. And so in any case, for the numbers that I've shared with you so far, that's only, if we take 1 bit of encryption and we have to, and then we decrypt it for these values, where it takes 2.5 days to do each one of them. That's only 148 bits of information we get decrypted per year. That's only 146. And so let's go to 2031, and like for the values that I said earlier, it takes a year to make a quantum computer. Well, rounding it down to a year. So we now have 146 bits of information times 10 computers. That's only 1,460 encrypted bits of data. Many of our own personal computers are doing that much in a day. And so you can see this value is almost nothing. Stay with me. We've got another 3 or 4 parameters that need to be considered as well. Next, McKinsey also estimated the cost to run a quantum computer to decrypt each encrypted bit would be about $64,000 US dollars for each bit. So for a year, that's going to be $9 million, a little bit over $9 million. And so have all 10 of those computers running at once, it's going to be $93 million. In any case, obviously, this is a value that essentially nation states are the only ones going to be able to afford, but yet there's more. And please keep in mind all these different criteria. And so everyone's saying that that the internet's going to be destroyed soon and so on and so forth. For these values and so on, I'm claiming I'm mistaken. Stay with me, there's still some more. Next, availability. I've been claiming for years that if something like this is going to happen where the encrypted code can be cracked, can be decrypted by anyone that has a computer and the knowledge how to run it, is that is going to become very politically significant. About 2 or 3 months ago, I was in a conference with Ilyas Khan, the co-founder of Quantinuum, and he stated what I have been stated for years also, and we discussed it, and there was nothing to disagree about, and that is when it becomes available, it becomes very politically significant. What will happen in authoritarian countries is they will just confiscate the equipment and that's it, and we won't know anything about it. In non-authoritarian countries, in other words, all of Western Europe, United States, Australia, and so on, and many other countries, I will use United States legal terms, but so translate it to whatever your country does, is that sure, they could confiscate it for national security reasons, but I would think the ideal way to do it, again, in the United States, to stay per laws and not upset people as much, and staying with my 2030 estimate, 2029, the United States government issues to all quantum companies that are headquartered in the United States a document that states something to the effect of, here is a mandatory contract. When you feel that you're getting close, like a couple of months ahead of being able to decrypt.
وانا راكن في حته ابعد من بيته فانا بتمشى اكتر منه. لا الحمد لله جبت ثاني. وديتك في السابعه.
Can you mute them so that
كريم صوتي.
Okay. Are they muted? Can you hear me? Did you mute me also?
No, we can hear you.
What's that?
We can hear you.
Okay, good. Thank you. So in non-authoritarian countries, again, United States, I would think the ideal way would be, like I said, they would issue a mandatory contract that a couple of months before a manufacturer feels that they will be reaching the capability to track RSA 2048 encrypted code, is that company would then be put on a mute type of status. That is, they aren't permitted to announce any further progressions in their research and any accomplishments that they develop as well. Then, when their research computer does achieve that status, they will be put under a contract, a paid contract, and so it's not like their equipment's being stolen, but they're put under a mandatory contract that the U.S. government or whatever government is then paying them to use their computer in any way that they deem that they would care to do so. And so my contention is that all of these criteria have to be met, not before our internet is going to be crashed and destroyed as is being claimed so regularly on by many people on the internet. And so lastly, even then, who's going to be at risk? Defense departments, departments of treasury, and in other words, nation states where the money is manufactured, and central banks. In other words, if you don't have, money-wise, if you don't have either trillions of equivalent to trillions of US dollars or some type of secrets that are worth billions, if not trillions of dollars, that I contend that you're not going to be of interest. You're too small of a fish. And so with these numbers that I've shared with you, even if manufacturers were prepared to start making many of their top-end computers that could crack, that could decrypt encrypted code, I personally and professionally don't see how anything is going to be developing before 2035 and probably well beyond that. So, a short presentation, that's all I've got. Fire away with any questions what you might have.
Yeah, thanks, Greg, very much. Please feel free if you have questions. Okay, so just a thought from my side. So when do you personally expect this QD to happen? When the fault-tolerant quantum computer is around, or when do you personally envision it?
For the figures I've shared, the nation states will need to be concerned starting 2031 or thereabouts. But as far as you or I as an individual, I can't see it happening for at least another 5 and probably more realistically 10 years, even with fault-tolerant computers. There's just not going to be enough of them. It's because remember, at least the presumptions that most people seem to make when they're saying that the encryption is going to be decrypted is that there are going to be thousands, if not millions, of computers to be able to run these calculations, as is done right now, as we're discussing here. Like every one of us have our own a computer to run it on. Well, and in this group, we probably have 3 or 4 for each individual. So what I'm getting at is that obviously won't be the case. There's only going to be single digits number or even double digits of computers for many years. And then the time that it's going to take to run them as well, and potentially more importantly, the amount of money that it's going to take to run them is going to make it impossible, except for nation states, essentially, to be able to crack, to decrypt only the most valuable of data.
And will this be coupled to the quality of the hardware? Like when for example, what any, for example, now with the fault tolerant, people envision, okay, if you have a certain quality qubits, you can start to do this application, this application, and this application. Would this, for example, the Q-Day would be coupled to a certain quality of the qubits, or the larger the larger the number of qubits, this will enable the for example the security threat from quantum computers?
Yes, of course it will, and along those lines, it will be exponentially increasing in time, the amount of time it will take to decrypt an encrypted bit of any sort. I fully agree. I don't know when that will be, but again, from what I'm seeing and from what I'm hearing, is even get close to this is going to be 2030, and then one has to produce those computers on top of that. That's the reason I'm saying 2031, because otherwise you have a lab computer, and as we all know, lab computers are spread out all over the room, and you're not going to be running those for these type of calculations because it'll break half the time. Well, not break, but the maintenance on how it's going to be astronomical. So even let's say if we're a major international bank, I couldn't see, let's say we're IBM IBM. And so we've got millions, I mean, hundreds of millions of dollars behind us. And we can see that we're making our time schedule, meaning 2019, we're going to be able to have a quantum computer that will be strong enough to decrypt an RSA 2048 code. All right. So they do like any wise company would do. They start buying materials 6 to 12 months in advance. They get the production lines going and so on and so forth. I'm stating that there won't be enough materials. They won't have the space to do it and so on and so forth. And even though they're going to have there's 250 countries in the world, they're going to have immediately a 250 clients, and obviously richer countries, Western Europe, United States, are going to be willing to buy a few of them. And so they can sell as many as they can manufacture as fast as they could. My point is, look at these numbers that I've shared with you. Is that those, 1,400 in a year? And so let's multiply that by 100 or 1,000. You're still not going to have much encryption going on. And I'm starting from the basis also of harvest now and decrypt later. If we've got to go through and we had to decrypt this conversation this presentation that we have right now, that's going to real time. And so this is now, I've got to have, what are there, how many people are there here? Whatever, 30, 40 of us. And so you're going to have to decrypt all those. And then you've got the TLS that starts the handshaking, and then you've got the body of it and all that's going on there. That's going to be impossible to do it live is my point. I can't see that in anything less than 2040.
Yeah, that's a good
even with the fault tolerant. Fault tolerant is going to start to bump us close to that, but do you see what these numbers that I'm sharing? It's not going to be anytime soon. That's for sure.
Yeah, that's a great insight indeed, because people are rushing the judgment that this will happen tomorrow or next week. But of course, there is more depth and technical depth on how this is could be executed.
What I always claim is just to look under the covers. In other words, just go one level deep whenever there's when there's starting to be such information spread about and everybody gets scared or excited or both, is just to look at it once, just to do a superficial look at something. And it's always been quite illustrative to me and set me at ease, because as has always happened, it's usually nonsense. And so again, for you and me, I can't imagine it being at least until the end of 2030s. I think Jan has a question. Thanks for your help earlier.
I wanted to introduce Jan is gonna join our Q&A session. So I'm sharing my screen quickly. So yes, Jan is of course a managing partner in Bibliotheca, which is Data Analysis Center for Life Sciences. I was also founder and owner, providing data analysis service for various industries. He has several current projects spanning from the focus on machine learning and the quantum machine learning applications, including quantum machine learning and spectrum analysis, classical machine learning for weather forecasting and Earth observations. And also he has previous projects involved HPC deployment for radio astronomy, yielding forecasting for potato crops, larger scale storage system design for HPC, and advanced semiconductor technology for low noise radio receiver. And of course he has extensive experience, worked for large IT systems and consulting firms since 1983, and he's physicist by training, graduated from Delft in the Netherlands. Okay, please, Jan. The floor is yours.
Good evening, good afternoon, people in the US, and good night, perhaps people more in Asia. I hear what Greg is stating, and I think also what Taha was telling, that it will take some time before there are real quantum computers that will really be able to decrypt data, with conventional that are encrypted with the current conventional protocols. Still,
Jan, it's not just the computers. I mean, I think all of us in this group are probably more, let's say, attuned or can make a better guess than probably most people in the world can, because this is what we do. I'm saying that there are another 3 or 4 criteria that are never brought up, that any one of those are going to be showstoppers. I mean, the amount of money it's going to cost to run one of these computers for that amount of time. Number 2, how little data is going to be acquired out of that. And you're going to have done so much pre-work before then. Like I said, harvest now, decrypt later, almost always, because otherwise it's going to take you almost all of your calculating capabilities for a year just to get to the core one that you need, and so on. And then you've got political problems. And so what I'm saying is that all of us, of course, are techies, and so we're addressing it from the technical standpoint, but I'm saying that it's much, much more complex, but there are many more layers involved, that it's not going to be anything nearly as bad as being forecast and doom and gloom tomorrow, like Taha was saying, tomorrow or the next week.
I agree with your considerations. Yeah,
Thank you.
I definitely don't want to make the issue smaller than it is. Yeah. Still, some companies, healthcare providers, or financial companies, banks, or government institutions will have data that is very important. Yeah.
Yes.
And so for those institutions, it's a no-brainer that they should prepare themselves, I would say.
Agreed.
Even if it takes a very long time.
Agreed. Because
because go ahead.
To elaborate on that, because this is a conversation I have in this, because I do a lot with cybersecurity groups as well, is that one of the big questions one has is that, let's say I have the data on how to make an atomic bomb. I'm just as an example, I mean, it could be whatever, but and this is still fairly valuable on the international market. That's right now today. Will it be valuable 10 years from now when this decryption is possible? And so that's the other criteria that I didn't bring up, is that what will be the actual value of your data when this comes about? So there's so there's yet another point I would care to add to it as well.
I mean, that's another thing. I don't want to dispute about that. Yeah. But there's another aspect to it. Storing data is really cheap these days. Yeah. And I guess it will get even cheaper. Yeah. So copy now, store it now, and decrypt later is a good business case if you have enough money and if you have enough time to wait. Yeah. And if you have enough plans to analyze your data. Yeah. So I don't underestimate that threat. Yeah, I would say. Yeah. Then there's another aspect that has to do with trust and reputation, and potential misuse of personal data. Yeah. And I can give you an example that is that we have in the Netherlands today, since a couple of weeks. A normal medical laboratory was infiltrated, and somebody copied data of patients, and a very, very large volume of data with a very high number of individuals. Yeah. I mean, in my professional thing, I mean, you really experience it, and every time I really wonder what the hell the people have been doing in order to protect themselves and to prepare themselves for such a thing. And still it happens, yeah. And then you can say, well, I mean, they are bad luck, but it's for those individual people, all those individuals who have lost their personal data that is now somewhere on the dark web, yeah, who run the risk of misuse of their identity, yeah. I mean, that is really a problem, yeah. Although on a global scale, you can say, well, I mean, they have bad luck, but I mean, for those people, it's really a very bad situation, yeah.
I think you bring up a good point, Jan, is that of the three categories I said that should be concerned, I need to add a fourth. Not so much what you're saying about personal information, because most of us, unless we get older, our personal information, especially when we're younger, I wouldn't have cared because you aren't going to, I mean, I'm going to have changed it probably 2 or 3 times over in 10 years. I mean, so what? Here, I'll give it to you right now, encrypted. And I mean, you aren't going to do anything by that time. That's going to be meaningless. But the part that you've said implicitly is with the health data of a person. Obviously, that's going to last more than a decade. And so the information about a person's physical health, you know, height, weight, so on and so forth, as well as their illnesses and a variety of other things. One specifically that I can think of that most certainly many insurance companies have been busted on here in the United States over many times over, is that what if that data goes out from all those people that you just mentioned, Jan, and every insurance company now has that in the United States. Well, they're going to kick out they're going to make up whatever excuse, whatever lie they want and say, no, we can't insure you because they have this data about that person's health from way back then, and it's the type of illness that isn't going to go away in somebody's lifetime, and that insurance company feels that it's too high a risk, and so they won't. And almost always is that if one insurance company says that, all the rest of them will say it too. Is that person will no longer be able to get health insurance of any sort. I mean, universal health and so on, but that's an example. But I'm just saying,
yeah,
you can use that with other things as well.
That is a very real case, yeah.
Yes, yes.
And I mean, so I can only recommend to every company, every institution, make sure you do all the encryption that you should be doing. Make sure that you have a real, genuine, detailed plan for migration to the next generation of encryption protocols and the post-quantum cryptography protocols, and start implementing that plan, yeah, because it will take a long time. It will take a long time.
Yes.
There are so many instances, so many lines, so many programs, data files, connections, small devices, big devices, large systems. Everywhere you need to upgrade the little programs, the firmware, the whatever, yeah, and you need to test it. So it will take a long time to migrate, yeah, and I can assure you, I mean, I'm from a technology point of view, I'm optimistic about quantum computing. That is my personal view. I may be wrong, but what I've seen in the last couple of years and the rate of progress that we are seeing these days, since I would say since last year, it's very impressive. So I believe when companies say they will have a first fault-tolerant quantum computer around 2030, 2031. Yeah, I do believe them. Yeah, and yeah, I mean, and then it will speed up once you can do fault-tolerant quantum computing. The progress will be even faster. Yeah. So that's how I see it, Greg.
And so, Jan, as you put in your question, is per what I'm sharing with everyone is that all that we're doing now shouldn't be changed. It's just the fervent part of it, the scaring part of it, the it's going to happen tomorrow part is unrealistic and invalid. That's the only thing that I'm saying that one should change is to get the emotions out of it, because when we look at it and analyze all the data, we can see that it's not going to happen tomorrow. It's still, at least with even the best of figures, 5 years out, and most certainly personally, it's going to be longer than that. And to continue doing good security practices now, that is making sure your data is secure and so on. So yes, I agree.
And in fact, I mean, I also think that it's not happening tomorrow. So, and even once those first fault-tolerant quantum computers will be available around the end of this decade, yeah, then those machines will be used for hopefully useful business applications, yeah, and not so. I mean, I guess not the capacity will be used to start decrypting the personal healthcare records, I guess. But still, yeah, it could happen at some stage after, let's say, 2030, 2033, 2034. Yeah. And what I also see in practice is that people are not deploying the state of the art in security. Yeah, there are some ideas of you cannot do it, or you are always late. I mean, that is not true. If you really deploy what is available today, yeah, and you keep up to date, then you can really protect yourself much better than what is happening in practice. Yeah. I mean, the example that I mentioned of this laboratory in the Netherlands, that should never have happened. Yeah. I don't know what they have done, so I'm not involved. So I don't know the details, but I'm really very surprised of what has happened over there. Yeah. So that's it for the moment. Yeah. Taha, I don't know how you want to proceed. Do you have other questions or?
Yeah, so thanks, Jan, and of course, thanks, Greg, for the nice presentation and for also the insights about the realistic view of the Q day, which is important for those who rush also reading things. And thanks, everyone. I would like to thank all the speakers and all the guests that were there, starting from Salim Higazi and also Randy Kyong, Alan Chansey, and Greg Pitts, and also Jan Blomert, who joined our Q&A session. And I'd like to thank Bibliotheca Alexandrina, including Engineer Yusuf Al-Dakar, who's also a co-partner in these nice monthly events where we meet and exchange nice ideas. So thanks, everyone, and yeah, so wish you great afternoon, great evening, and a great day, depending on the time zone, as Jan indicated.
Right. Bye-bye.
And of course, see you next week for those who are gonna be in person in Alexandria. So see you, and hopefully we meet for coffee.
Yeah.
Okay. Yeah. Thanks. Bye.